The last chapter of this course is discussion about the other test types. In this chapter we will be discussing different system and acceptance test types. Software development is largely a process of communicating information about the eventual program and translating this information from one form to another. For that reason, the vast majority of software errors can be attributed to breakdowns, mistakes, and noise during the communication and translation of information. This view of software development is illustrated in figure on this slide, a model of the development cycle for a software product. The flow of the process can be summarized in 7 steps. 1. The program user's needs are translated into a set of written requirements. These are the goals for the product. 2. The requirements are translated into specific objectives by assessing feasibility and cost, resolving conflicting requirements, and establishing priorities and trade-offs. 3. The objectives are translated into a precise product specifica. Tie-in, viewing the product as a black box and considering only its interfaces and interactions with the end user. This description is called the external specification. 4. If the product is a system such as an operating system, flight control system, database management system, or employee personnel system, rather than a program, compiler, payroll program, word processor, the next process is system design. This step partitions the system into individual programs, components, or subsystems and defines their interfaces. 5. The structure of the program or programs is designed by specifying the function of each module, the hierarchical structure of the modules, and the interfaces between modules. 6. A precise specification is developed that defines the interface to and function of each module. 7. Through one or more substeps, the module interface specification is translated into the source code algorithm of each module. Here's another way of looking at these forms of documentation. Requirements specify why the program is needed. Objectives specify what the program should do and how well the program should do it. External specifications define the exact representation of the program to users. Documentation associated with the subsequent processes specifies, in increasing levels of detail, how the program is constructed. Given the premise that the 7 steps of the development cycle involve communication, comprehension, and translation of information, and the premise that most software errors stem from breakdowns in information handling, there are 3 complementary approaches to prevent and/or detect these errors. First, we can introduce more precision into the development process to prevent many of the errors. Second, we can introduce, at the end of each process, a separate verification step to locate as many errors as possible before proceeding to the next process. This approach is illustrated in figure on this slide. For instance, the external specification is verified by comparing it to the output of the prior stage, the statement of objectives, and feeding back any discovered mistakes to the external specification process. Use the code inspection and walkthrough methods in the verification step at the end of the 7th process. The third approach is to orient distinct testing processes toward distinct development processes. That is, focus each testing process on a particular translation step, thus focusing it on a particular class of errors. This approach is illustrated in figure on this slide. The testing cycle has been structured to model the development cycle. In other words, you should be able to establish a one-to-one correspondence between development and testing processes. For instance, the purpose of a module test is to find discrepancies between the program's modules and their interface specifications. The purpose of a function test is to show that a program does not match its external specifications. The purpose of a system test is to show that the product is inconsistent with its original objectives. The advantages of this structure are that it avoids unproductive redundant testing and prevents you from overlooking large classes of errors. For instance, rather than simply labeling system testing as the testing of the whole system, and possibly repeating earlier tests. System testing is oriented toward a distinct class of errors, those made during the translation of the objectives to the external specification, and measured with respect to a distinct type of documentation in the development process. The higher-order testing methods shown in Figure 6.3 are most applicable to software products, programs written as a result of a contract or programs intended for wide usage, as opposed to experimental programs or programs written for use only by the program's author. Programs not written as products often do not have formal requirements and objectives. For such programs, the function test might be the only higher-order test. Also, the need for higher-order testing increases as the size of the program increases. The reason is that the ratio of design errors made in the earlier development processes, to coding errors is considerably higher in large programs than in small programs. Function testing is a process of attempting to find discrepancies between the program and the external specification. An external specification is a precise description of the program's behavior from the point of view of the end user. Except when used on small programs, function testing is normally a black box activity. That is, you rely on the earlier module testing process to achieve the desired white box logic coverage criteria. To perform a function test, the specification is analyzed to derive a set of test cases. The equivalence partitioning, boundary value analysis, cause-effect graphing, and error guessing methods are especially pertinent to function testing. Keep track of which functions have exhibited the greatest number of errors. This information is valuable because it tells us that these functions probably also contain the preponderance of as yet undetected errors. Remember to focus a sufficient amount of attention on invalid and unexpected input conditions. Finally, as always, remember that the purpose of the function test is to expose errors and discrepancies with the specification, not to demonstrate that the program matches its external specification. System testing is the most misunderstood and most difficult testing process. System testing is not a process of testing the functions of the complete system or program, because this would be redundant with the process of function testing. System testing has a particular purpose: to compare the system or program to its original objectives. Given this purpose, two implications are as follows. 1. System testing is not limited to systems. If the product is a program, system testing is the process of attempting to demonstrate how the program, as a whole, does not meet its objectives. 2. System testing, by definition, is impossible if there is no set of written, measurable objectives for the product. In looking for discrepancies between the program and its objectives, focus on translation errors made during the process of designing the external specification. This makes the system test a vital test process because in terms of the product, the number of errors made, and the severity of those errors, this step in the development cycle usually is the most error-prone. It also implies that, unlike the function test, the external specification cannot be used as the basis for deriving the system test cases, since this would subvert the purpose of the system test. On the other hand, the objectives document cannot be used, by itself, to formulate test cases, since it does not, by definition, contain precise descriptions of the program's external interfaces. We solve this dilemma by using the program's user documentation or publications. Design the system test by analyzing the objectives. Formulate test cases by analyzing the user documentation. This has the useful side effect of comparing the program to its objectives and to the user documentation, as well as comparing the user documentation to the objectives, as shown in Figure 6.4 illustrates why system testing is the most difficult testing process. The leftmost arrow in the figure, comparing the program to its objectives, is the central purpose of the system test, but there are no known test case design methodologies. The reason for this is that objectives state what a program should do and how well the program should do it, but they do not state the representation of the program's functions. For instance, the objectives for the display command might have read as follows: A command will be provided to view, from a terminal, the contents of main storage locations. Its syntax should be consistent with the syntax of all other system commands. The user should be able to specify a range of locations via an address range or an address and account. Sensible defaults should be provided for command operands. Output should be displayed as multiple lines of multiple words in hexadecimal, with spacing between the words. Each line should contain the address of the first word of that line. The command is a trivial command, meaning that under reasonable system loads, it should begin displaying output within 2 seconds, and there should be no observable delay time between output lines. A programming error in the command processor should, at the worst, cause the command to fail the system, and the user's session must not be affected. The command processor should have no more than one user-detected error after the system is put into production. Given the statement of objectives, there is no identifiable methodology that would yield a set of test cases other than the vague but useful guideline of writing test cases to attempt to show that the program isn't consistent with each sentence in the objectives statement. Hence, a different approach to test case design is taken here. Rather than describing a methodology, distinct categories of system test cases are discussed. Because of the absence of a methodology, system testing requires a substantial amount of creativity. In fact, the design of good system test cases requires more creativity, intelligence, and experience than are required to design the system or program. Facility testing. The most obvious type of system testing is the determination of whether each facility or function, but the word function is not used here to avoid confusing this with function testing, mentioned in the objectives, was actually implemented. The procedure is to scan the objectives sentence by sentence, and when a sentence specifies a what, for example, syntax should be consistent, user should be able to specify a range of locations. Determine that the program satisfies the what. This type of testing often can be performed without a computer. A mental comparison of the objectives with the user documentation is sometimes sufficient. Nonetheless, a checklist is helpful to ensure that you mentally check the same objectives the next time you perform the test. Volume testing. A second type of system testing is subjecting the program to heavy volumes of data. For instance, a compiler would be fed an absurdly large source program to compile. A linkage editor might be fed a program containing thousands of modules. An electronic circuit simulator would be given a circuit containing thousands of components. An operating system's job queue would be filled to capacity. If a program is supposed to handle files spanning multiple volumes, enough data is created to cause the program to switch from one volume to another. In other words, the purpose of volume testing is to show that the program cannot handle the volume of data specified in its objectives. Since volume testing obviously can require significant resources in terms of machine and people time, you can't go overboard. However, every program must be exposed to at least a few volume tests. Stress testing. Stress testing subjects the program to heavy loads or stresses. This should not be confused with volume testing. A heavy stress is a peak volume of data or activity encountered over a short span of time. An analogy would be evaluating a typist. A volume test would determine whether the typist could cope with a draft of a large report. A stress test would determine whether the typist could type at a rate of 50 words per minute. Because stress testing involves an element of time, it is not applicable to many programs, for example, a compiler, or a batch processing payroll program. It is applicable, however, to programs that operate under varying loads, or interactive, real-time, and process control programs. If an air traffic control system is supposed to keep track of up to 200 planes in its sector, you could stress test it by simulating the existence of 200 planes. Since there is nothing to physically keep a 201st plane from entering the sector, a further stress test would explore the system's reaction to this unexpected plane. An additional stress test might simulate the simultaneous entry of a large number of planes into the sector. If an operating system is supposed to support a maximum of 15 multi-program jobs, the system could be stressed by attempting to run 15 jobs simultaneously. Stress a pilot training aircraft simulator by determining the system's reaction to the trainees forcing the rudder left pulling back on the throttle, lowering the flaps, lifting the nose, lowering the landing gear, turning on the landing lights, and banking left, all at the same time. Such test cases might require a four-handed pilot, or, realistically, two test specialists, in the cockpit. You might stress test a process control system by causing all of the monitored processes to generate signals simultaneously. A telephone switching system is stressed by routing to it a large number of simultaneous phone calls. One of the common recipients of stress testing is web-based applications. Here you want to ensure that your application and hardware can handle some volume of concurrent users. You could argue that you may have millions of people accessing the site at one time, but that is not realistic. You need to understand your audience, then design a stress test to represent the maximum number of users you think will use your site. Although many stress tests do represent conditions that the program likely will experience during its operation, other stress tests may truly represent never-will-occur situations, but this does not imply that these tests are not useful. If these impossible conditions detect errors, the test is valuable, because it is likely that the same errors might also occur in realistic, less stressful situations. Usability testing. Another important category of system test cases is an attempt to find human factor, or usability, problems. Today's software systems, particularly those designed for a mass commercial market, generally have undergone extensive human factor studies, and modern programs, of course, benefit from the thousands of programs and systems that have gone before. Nevertheless, an analysis of human factors is still a highly subjective matter. Here's our list of considerations that might be tested. 1. Has each user interface been tailored to the intelligence, educational background, and environmental pressures of the end user? 2. Are the outputs of the program meaningful, non-abusive, and devoid of computer gibberish? 3. Are the error diagnostics, such as error messages, straightforward? Or does the user need a PhD in computer science to comprehend them? Mass market systems do better today, but you still will encounter unhelpful messages such as an unknown error has occurred, or this program has encountered an error and must be restarted. Programs you design yourself are under your control and should not be plagued with such useless messages. Even if you didn't design the program, if you are on the testing team, you can push for improvements in this area of the human interface. 4. Does the total set of user interfaces exhibit considerable conceptual integrity and underlying consistency and uniformity of syntax, conventions, semantics, format, style, and abbreviations? 5. Where accuracy is vital, such as in an online banking system, is sufficient redundancy present in the input? For example, such a system should ask for an account number, a customer name, and a PIN, personal identification number, to verify that the proper person is accessing account information. 6. Does the system contain an excessive number of options, or options that are unlikely to be used? One trend in modern software is to present to the user only those menu choices they are most likely to use, based on software testing and design considerations. Then a well-designed program can learn from the user and begin to present those menu items that individual users frequently access. Even with such an intelligent menu system, successful programs still must be designed so that accessing the various options is logical and intuitive. Security testing. Because of society's increasing concern about privacy, many programs have specific security objectives. Security testing is the process of attempting to devise test cases that subvert the program's security checks. For example, you could try to formulate test cases that get around an operating system's memory protection mechanism. You can try to subvert a database management system's data security mechanisms. One way to devise such test cases is to study known security problems in similar systems and generate test cases that attempt to demonstrate similar problems in the system you are testing. For example, published sources in magazines, chat rooms, or news groups frequently cover known bugs in operating systems or other software systems. By searching for security holes in existing programs that provide services similar to the one you are testing, you can devise test cases to determine whether your program suffers from similar problems. Web-based applications often need a higher level of security testing than do most applications. This is especially true of e-commerce sites. Although sufficient technology, namely encryption, exists to allow customers to complete transactions securely over the Internet, you should not rely on the mere application of technology to ensure safety. In addition, you will need to convince your customer base that your application is safe, or you risk losing customers. Performance testing. Many programs have specific performance or efficiency objectives, stating such properties as response times and throughput rates under certain workload and configuration conditions. Again, since the purpose of a system test is to demonstrate that the program does not meet its objectives, test cases must be designed to show that the program does not satisfy its performance objectives. Storage testing. Similarly, programs occasionally have storage objectives that state, for example, the amount of main and secondary memory the program uses, and the size of temporary or spill files. You should design test cases to show that these storage objectives have not been met. Configuration testing. Programs such as operating systems, database management systems, and message switching programs support a variety of hardware configurations, including various types and numbers of I/O devices and communications lines, or different memory sizes. Often the number of possible configurations is too large to test each one, but at the least, you should test the program with each type of hardware device and with the minimum and maximum configuration. If the program itself can be configured to omit program components, or if the program can run on different computers, each possible configuration of the program should be tested. Today, many programs are designed for multiple operating systems, for example, so if you are testing such a program, you should test it with all of the operating systems for which it was designed. Programs designed to execute within a web browser require special attention, since there are numerous web browsers available, and they don't all function the same way. In addition, the same web browser will operate differently on different operating systems. Compatibility/configuration/conversion testing. Most programs that are developed are not completely new. They often are replacements for some deficient system. As such, programs often have specific objectives concerning their compatibility with, and conversion procedures from, the existing system. Again, in testing the program to these objectives, the orientation of the test cases is to demonstrate that the compatibility objectives have not been met and that the conversion procedures do not work. Here you try to generate errors while moving data from one system to another. An example would be upgrading a database management system. You want to ensure that your existing data fit inside the new system. Various methods exist to test this process, however, they are highly dependent on the database system you employ. Instability testing. Some types of software systems have complicated installation procedures. Testing the installation procedure is an important part of the system testing process. This is particularly true of an automated installation system that is part of the program package. A malfunctioning installation program could prevent the user from ever having a successful experience with the main system you are charged with testing. A user's first experience is when he or she installs the application. If this phase performs poorly, then the user/customer may find another product or have little confidence in the application's validity. Reliability testing. Of course, the goal of all types of testing is the improvement of the program reliability. But if the program's objectives contain specific statements about reliability, specific reliability tests might be devised. Testing reliability objectives can be difficult. For example, a modern online system such as a corporate wide area network, WAN, or an internet service provider, ISP, generally has a targeted uptime of 99.97% over the life of the system. There is no known way that you could test this objective with a test period of months, or even years. Today's critical software systems have even higher reliability standards, and today's hardware conceivably could be expected to support these objectives. Programs or systems with more modest mean time between failures, MTBF, objectives, or reasonable, in terms of testing, operational error objectives can potentially be tested. An MTBF of no more than 20 hours, or an objective that a program should experience no more than 12 unique errors after it is placed into production. For example, presence testing possibilities, particularly for statistical, program proving, or model-based testing methodologies. Recovery testing. Programs such as operating systems, database management systems, and teleprocessing programs often have recovery objectives that state how the system is to recover from programming errors, hardware failures, and data errors. One objective of the system test is to show that these recovery functions do not work correctly. Programming errors can be purposely injected into a system to determine whether it can recover from them. Hardware failures such as memory parity errors or I/O device errors can be simulated. Data errors such as noise on a communications line or an invalid pointer in a database can be created purposely or simulated to analyze the system's reaction. One design goal of such systems is to minimize the mean time to recovery, MTR. Downtime often causes a company to lose revenue because the system is inoperable. One testing objective is to show that the system fails to meet the service level agreement. For often, the MTTR will have an upper and lower boundary, so your test cases should reflect these bounds. Serviceability testing. The program also may have objectives for its serviceability or maintainability characteristics. All objectives of this sort must be tested. Such objectives might define the service aids to be provided with the system, including storage dump programs or diagnostics, the mean time to debug an apparent problem, the maintenance procedures, and the quality of internal logic documentation. Documentation testing. The system test also is concerned with the accuracy of the user documentation. The principal way of accomplishing this is to use the documentation to determine the representation of the prior system test cases. That is, once a particular stress case is devised, you would use the documentation as a guide for writing the actual test case. Also, the user documentation should be the subject of an inspection, checking it for accuracy and clarity. Any examples illustrated in the documentation should be encoded into test cases and fed to the program. Procedure testing. Finally, many programs are parts of larger, not completely automated systems involving procedures people perform. Any prescribed human procedures, such as procedures for the system operator, database administrator, or end user, should be tested during the system test. For example, a database administrator should document procedures for backing up and recovering the database system. If possible, a person not associated with the administration of the database should test the procedures. However, a company must create the resources needed to adequately test the procedures. These resources often include hardware and additional software licensing. Acceptance testing. Returning to the overall model of the development process shown in Figure 6.3, you can see that acceptance testing is the process of comparing the program to its initial requirements and the current needs of its end users. It is an unusual type of test in that it usually is performed by the program's customer or end user, and normally is not considered the responsibility of the development organization. In the case of a contracted program, the contracting user organization performs the acceptance test by comparing the program's operation to the original contract. As is the case for other types of testing, the best way to do this is to devise test cases that attempt to show that the program does not meet the contract. If these test cases are unsuccessful, the program is accepted. In the case of a program product, such as a computer manufacturer's operating system or compiler, or a software company's database management system, the sensible customer first performs an acceptance test to determine whether the product satisfies its needs. Installation testing. The remaining testing process in Figure 6.3 is the installation test. Its position in Figure 6.3 is a bit unusual, since it is not related, as all of the other testing processes are, to specific phases in the design process. It is an unusual type of testing, because its purpose is not to find software errors, but to find errors that occur during the installation process. Many events occur when installing software systems. A short list of examples includes the following. User must select a variety of options. Files and libraries must be allocated and loaded. Valid hardware configurations must be present. Programs may need network connectivity to connect to other programs. Installation tests should be developed by the organization that produced the system, delivered as part of the system, and run after the system is installed. Among other things, the test cases might check to ensure that a compatible set of options has been selected, that all parts of the system exist, that all files have been created and have the necessary contents, and that the hardware configuration is appropriate.